Tonight, we're wandering into territory that needs no introduction because you know it intimately, yet remains curiously mysterious. It's something you do every single day, or night, rather, without fanfare or celebration. There are no monuments erected to it, no parades in its honor. It simply happens, reliably, predictably, like breathing or blinking. Take a slow breath now. Feel your eyelids growing just a little heavier. We're going to explore sleep itself tonight. Not the dramatic aspects of sleep, not the fascinating disorders or the vivid dreams that capture our imagination, but sleep in its most fundamental, ordinary, and yes, perhaps even boring form. The kind of sleep that unfolds night after night, cycle after cycle, stage after stage, with the rhythmic predictability of waves lapping at a shore. There's something oddly comforting about the mundane, isn't there? In a world that constantly demands our attention, that floods us with novelty and urgency, sleep remains delightfully, reassuringly dull. It asks nothing of you except that you lie down, close your eyes, and let it happen. No decisions to make, no problems to solve, no performances to give. Just the quiet descent into unconsciousness, followed hours later by the gentle return to waking life. Tonight, we'll trace sleep through its many dimensions. We'll move slowly through its history, from ancient philosophical musings to modern neuroscience. We'll examine the machinery that governs it, the stages that compose it, the chemicals that induce it, and the consequences that follow when we lose it. We'll explore the psychology of monotony and repetition, and how they relate to our need for rest. But we'll do all of this at a pace that honors sleep's own unhurried nature, letting each idea settle before moving to the next, allowing information to wash over you like a warm tide. The historical development of sleep understanding. Long before electrodes measured brain waves or scientists mapped neural circuits, humans pondered the mystery of sleep. In the ancient world, sleep occupied a curious space between the physical and the spiritual, between the mundane necessity of rest and the profound experience of dreams. The ancient Egyptians built temples dedicated to sleep and dreams. These weren't grand philosophical institutions, but practical places where people sought healing and guidance. Priests would interpret dreams, believing them to be messages from the gods. The god Serapis presided over these temples, and those who entered hoped to receive divine wisdom during their slumber. Sleep in this context wasn't merely rest. It was a gateway to another realm, a time when the boundaries between mortal and divine grew thin and permeable. In Mesopotamia, similar beliefs prevailed. The Epic of Gilgamesh, one of humanity's oldest surviving texts, speaks of sleep as intertwined with mortality itself. When Gilgamesh seeks immortality, he's challenged to stay awake for 6 days and 7 nights. His failure demonstrates sleep's inescapable power over mortal beings. Sleep becomes a symbol of human frailty, a reminder that we are not gods, that we must submit to our biological nature, no matter how much we might wish otherwise. The ancient Greeks approached sleep with their characteristic love of systematic inquiry. They didn't abandon the spiritual dimension entirely, but they began asking practical questions. Hippocrates, often called the father of medicine, who lived from around 460 to 370 BCR, wrote extensively about sleep's role in health. He observed that sleep patterns could indicate illness, that disrupted sleep often preceded or accompanied disease. His writings demonstrate a remarkably modern understanding that sleep wasn't separate from health, but integral to it. Good sleep, he suggested, was as essential as good food or clean water. Aristotle, that systematic thinker who catalogued everything from animals to ethics, developed a theory of sleep that seems quaint to modern ears but represented serious scientific thinking for its time. He proposed that sleep resulted from the accumulation of warm vapors rising from digested food. These vapors would travel to the brain, cooling there and inducing drowsiness. Upon waking, the body would warm again, and the cycle would continue. While the specifics were incorrect, we might see in Aristotle's thinking an early intuition towards homeostatic principles. The idea that something builds up during wakefulness and must be cleared during sleep. Though his mechanism was far from accurate, the underlying concept of accumulation and clearance bears a faint resemblance to what we now understand about sleep pressure. The Roman philosopher Lucretius, writing in the 1st century BCE, observed that animals and humans alike experienced periods of rest and activity. He noted that even the smallest creatures seemed to need sleep, which led him to propose that it served some fundamental biological purpose. While he couldn't know the molecular or cellular mechanisms, his observations pointed towards sleep's universality across species. Sleep, he reasoned, must be as basic to life as eating or reproduction, an insight that centuries later would find support in biological research. For many centuries after the fall of Rome, sleep research stagnated in Europe, though it continued in the Islamic world. Medieval European scholars were more concerned with the spiritual dimensions of sleep and dreams than with its biological basis. But the Renaissance brought renewed interest in empirical observation and systematic study. In the 17th century, René Descartes proposed a hydraulic theory of sleep. He suggested that the pineal gland, a small structure deep in the brain, acted as a valve controlling the flow of animal spirits through the nervous system. During wakefulness, these spirits flowed freely, animating the body. During sleep, the valve closed and the spirits retreated. Though mechanistically wrong, Descartes' focus on a specific brain structure as central to sleep control would prove prescient in an unexpected way. The pineal gland does indeed play a role in sleep regulation, though not in the way Descartes imagined. It produces melatonin, a hormone that helps regulate our sleep-wake cycles. But the actual orchestration of sleep involves far more than this single small gland. The 18th century brought the first glimmerings of modern sleep science. In 1729, a French astronomer named Jean-Jacques d'Ortuc de Mairan conducted a deceptively simple experiment. He placed a mimosa plant in constant darkness and observed that its leaves continued to open and close on a roughly 24-hour schedule. even without the cue of sunlight. This observation, while focused on plants rather than animals, hinted at something profound. Living organisms possess internal timekeepers, biological clocks that persist even without external cues. The 19th century saw accelerating progress. Scientists began linking sleep to brain function more explicitly. In 1845, a British physician named John Davy studied the relationship between body temperature and sleep, noting that temperature dropped during sleep and rose during wakefulness. This observation connected sleep to metabolic processes, suggesting that sleep served some regulatory function for the body's energy systems. Then, in the early 20th century, came breakthroughs that would transform sleep from philosophy to science. In 1924, German psychiatrist Hans Berger developed the electroencephalogram, or EEG, which could record the electrical activity of the brain through electrodes placed on the scalp. For the first time, scientists could observe what the brain was doing during sleep without disturbing the sleeper. Berger noticed that brain waves changed dramatically between wakefulness and sleep, becoming slower and more synchronized during rest. The true father of modern sleep research, however, was Nathaniel Kleitman, who established the first sleep laboratory at the University of Chicago in 1925. Kleitman and his students subjected themselves and volunteers to rigorous observation, documenting sleep patterns, testing the effects of sleep deprivation, and cataloging the various phenomena associated with sleep. His work established sleep as a legitimate field of scientific inquiry. Kleitman's dedication to understanding sleep bordered on obsession. He didn't merely study sleep from a distance. He lived it, breathed it, experimented with it on himself and his family. In 1938, he and his graduate student Bruce Richardson spent more than a month deep underground in Mammoth Cave, Kentucky, living in total darkness to test whether humans could adapt to a 28-hour day. The experiment was uncomfortable, isolating, and yielded mixed results. Richardson adapted somewhat to the altered schedule, while Kleitman's body stubbornly clung to its 24-hour rhythm. But it demonstrated the existence of an internal biological clock that persisted even without external time cues. The most significant discovery from Kleitman's laboratory came in 1953, when he and his graduate student, Eugene Aserinsky, identified a previously unknown phase of sleep characterized by rapid eye movements. They called it REM sleep, and its discovery revolutionized sleep science. Before REM was identified, researchers had assumed sleep was a uniform state of reduced brain activity. The discovery that the sleeping brain cycled through distinctly different phases, some involving brain activity nearly as intense as waking, transformed our understanding of what sleep actually is. Why does sleep exist at all? This question occupied Kleitman throughout his career, and it remains incompletely answered even today. Several theories have been proposed, though none has achieved complete consensus among researchers. Some scientists hypothesize that sleep serves primarily to conserve energy, allowing the body to reduce its metabolic demands during periods when activity would be inefficient or dangerous. Evidence for this theory includes the observation that sleep reduces body temperature and metabolic rate, though critics point out that the energy saved during sleep is minimal, roughly equivalent to a piece of toast. Another hypothesis suggests that sleep evolved primarily for safety, keeping animals inactive during times when they would be vulnerable to predators, or when environmental conditions made activity unproductive. A small animal, for instance, might be better off sleeping through the night than wandering in darkness where it could easily become prey. However, this theory struggles to explain why sleep makes animals even more vulnerable by reducing their awareness of threats. Current research increasingly supports the view that sleep serves multiple essential functions related to brain maintenance and optimization. During sleep, the brain appears to consolidate memories, transferring information from temporary storage to more permanent locations and integrating new experiences with existing knowledge. Sleep also seems crucial for clearing metabolic waste products from brain tissue, a function we'll explore in detail later. These functions may explain why even the simplest animals with nervous systems exhibit sleep-like states. Sleep might be less a luxury than a fundamental requirement for nervous system health. The architecture of sleep. When you fall asleep tonight, your brain won't simply switch off like a light. Instead, it will begin a carefully choreographed journey through several distinct states, each with its own characteristic patterns of brain activity, its own purposes, its own qualities. This journey repeats 4 or 5 times each night, in cycles lasting roughly 90 minutes, though the proportion of time spent in each stage shifts as the night progresses. Sleep researchers divide sleep into 2 main categories: REM sleep and non-REM sleep, abbreviated as NREM. Non-REM sleep is further divided into 3 stages, numbered 1 through 3, with each stage representing progressively deeper sleep. Stage 1, or N1, is the lightest sleep, the boundary between wakefulness and true sleep. It typically lasts only a few minutes at the beginning of each sleep cycle. During N1, brain waves slow from the rapid beta waves of alert wakefulness to the gentler alpha and theta waves. Your muscles relax, though they may occasionally twitch. You might experience those strange sensations of falling or floating that sometimes jerk you back to wakefulness. If someone speaks to you during N1, you might hear them and respond, though you probably won't remember the conversation later. This stage is fragile, easily disrupted, a tentative first step into the depths of sleep. Stage 2, or N2, represents true sleep, though still relatively light. N2 accounts for roughly half of your total sleep time across the night. During this stage, your heart rate slows, your body temperature drops, and your muscles relax further. Brain activity continues to slow, but it's punctuated by brief bursts of rapid waves called sleep spindles and occasional sharp waves called K-complexes. Research suggests these sleep spindles may play important roles in memory consolidation and in protecting sleep from external disturbances. During N2, you become less aware of your environment, more difficult to wake, more deeply separated from the waking world. Stage 3, or N3, is the deepest non-REM sleep, sometimes called slow wave sleep or delta sleep, because of the large, slow delta waves that dominate the EEG during this stage. This is the sleep that feels most like sleep, the profound unconsciousness that leaves you disoriented if awakened. During N3, blood pressure drops, breathing becomes slower and more regular, muscles relax completely, and the body becomes essentially unresponsive to external stimuli. A loud noise might not wake you, and if it does, you'll likely feel confused and groggy, struggling to orient yourself. Research associates this stage with the most dramatic physical restoration, tissue growth and repair, immune system strengthening, and energy restoration. N3. Sleep predominates in the first half of the night, with each successive cycle containing less of it. Then comes REM sleep, a state so different from the other stages that it almost deserves to be called something other than sleep. During REM, your brain becomes highly active, generating fast, desynchronized brain waves that resemble those of wakefulness more than sleep. Your eyes move rapidly behind closed lids, giving this stage its name. Your breathing becomes faster and more irregular. Your heart rate increases. Yet paradoxically, your voluntary muscles become temporarily paralyzed, unable to move except for occasional twitches. This paralysis appears to be protective, preventing you from acting out your dreams. Dreams occur in all sleep stages, but the most vivid, narrative, emotionally intense dreams happen during REM. The dream experience during REM tends to be bizarre, illogical, emotionally charged. Consciousness untethered from the constraints of waking logic and physics. Scientists believe REM sleep plays crucial roles in emotional regulation and certain types of memory processing, particularly the consolidation of procedural memories, how to do things rather than facts about things. These stages don't occur randomly. They follow a predictable sequence, repeating in cycles throughout the night. A typical cycle begins with 1 naira, progresses through 2 naira to 3 naira, then returns through 2 naira before entering REM. The entire cycle takes roughly 90 minutes, though this varies between individuals and across the lifespan. Early in the night, cycles contain more N3 sleep and less REM. As the night progresses, N3 becomes briefer or disappears entirely, while REM periods lengthen. Your longest, most dream-filled REM period typically occurs in the early morning hours, shortly before natural awakening. This architecture isn't arbitrary. Each stage appears to serve specific functions, and the cycling pattern seems important for those functions to occur properly. Disrupting this architecture by waking frequently, by preventing certain stages from occurring, or by compressing sleep time, can impair the restorative benefits of sleep, even if total sleep time seems adequate. The molecular machinery of sleep. Beneath the observable phenomena of sleep stages and cycles lies a vast molecular machinery that generates and regulates sleep. This machinery operates at multiple levels simultaneously. Neurotransmitters influencing neuronal activity, hormones coordinating body-wide responses, genes switching on and off in rhythmic patterns. Understanding this machinery helps explain not just what happens during sleep, but why sleep feels the way it does, why we can't simply choose to stay awake indefinitely, why even the strongest willpower eventually succumbs to sleep's demands. The pressure to sleep builds throughout the day through the accumulation of a molecule called adenosine. Research strongly suggests that adenosine plays a key role in generating sleep pressure, though scientists continue to refine their understanding of the exact mechanisms. Neurons use adenosine triphosphate, or ATP, as their primary energy currency. When ATP is broken down to release energy, one of the byproducts is adenosine. The longer you're awake, the more active your neurons are, the more ATP they consume, and the more adenosine accumulates in the brain. Adenosine binds to specific receptors on neurons, and this binding has an inhibitory effect, gradually reducing neuronal activity and promoting drowsiness. Evidence indicates that the accumulation of adenosine in certain brain regions, particularly the basal forebrain, is closely associated with the increasing desire to sleep. When you finally sleep, adenosine levels gradually decline as it's cleared from the brain, which may be part of why sleep reduces the pressure to sleep. You're literally clearing away the molecular signal that was demanding rest. This is why caffeine works as a stimulant. Caffeine molecules closely resemble adenosine molecules in shape, and they can bind to adenosine receptors without activating them. By occupying these receptors, caffeine blocks adenosine from binding, temporarily masking the sleepiness signal, even though adenosine continues accumulating. The caffeine doesn't make you less tired in any fundamental sense. It just prevents you from feeling how tired you actually are. When the caffeine wears off and adenosine finally binds to its receptors, the accumulated sleep debt hits all at once, producing the familiar caffeine crash. But adenosine is only one part of sleep regulation. The other major system is the circadian clock, the internal timekeeper that synchronizes sleep with the day-night cycle. Studies have shown that this clock operates independently of sleep pressure. It continues running even during prolonged wakefulness or sleep, ticking away according to its own approximately 24-hour rhythm. The master circadian clock resides in a tiny region of the brain called the suprachiasmatic nucleus, or SCN, located in the hypothalamus just above where the optic nerves cross. The SCN contains specialized neurons that generate rhythmic electrical activity without any external input. These neurons possess internal molecular loops, genes that encode proteins that eventually inhibit their own production, creating oscillations that take roughly 24 hours to complete. Research indicates that this self-sustaining rhythm continues even if these neurons are isolated in a laboratory dish, demonstrating that the clock is truly internal, not dependent on external signals. However, the SCN doesn't operate in complete isolation from the world. It receives direct input from specialized light-sensitive cells in the retina, allowing it to synchronize its internal rhythm with the external day-night cycle. When light hits these retinal cells, signals travel directly to the SCN, where they can shift the timing of the clock, advancing it if light comes in the morning, delaying it if light comes in the evening. This is how the circadian clock stays aligned with Earth's rotation, despite small imperfections in its timing. The SCN coordinates sleep timing by regulating multiple downstream systems. Current evidence suggests it influences the production of melatonin by the pineal gland, a hormone that rises in the evenings and helps prepare the body for sleep. It also modulates body temperature, which drops during typical sleep times. It influences the release of cortisol, which rises before normal wake time to help prepare the body for activity. These coordinated changes create windows of time when sleep comes easily and periods when staying awake is natural. Sleep occurs when both systems align. When adenosine has accumulated sufficiently to generate strong sleep pressure, and when the circadian clock has opened the gate for sleep. During the day, even if you're tired from adenosine accumulation, the circadian clock promotes wakefulness, making it difficult to fall into deep sleep. At night, when both systems favor sleep, unconsciousness comes easily and lasts for hours. Various neurotransmitters and neuromodulators orchestrate the transitions between sleep stages and between sleep and wakefulness. Studies indicate that during wakefulness, neurons in several brain regions release neurotransmitters that promote alertness. Norepinephrine from the locus coeruleus, serotonin from the raphe nuclei, histamine from the tuberomammillary nucleus, and orexin from the hypothalamus. These arousal systems work together to maintain the waking state. As sleep approaches, neurons in the ventrolateral preoptic nucleus, or VLPO, become active. Research suggests these neurons release the inhibitory neurotransmitter GABA, which suppresses the arousal systems, allowing sleep to begin. Once this switch flips, the brain rapidly transitions into sleep. The presence of these mutually inhibitory systems creates a kind of flip-flop switch. You're either awake or asleep, with relatively brief transitions between states, rather than gradual slides. REM sleep involves yet another set of neural circuits. Evidence indicates that neurons in the pons, a region of the brainstem, trigger REM sleep by releasing acetylcholine, which activates the thalamus and cerebral cortex, while simultaneously triggering the muscle paralysis characteristic of REM. The cycling between REM and NEM sleep involves complex interactions between multiple neurotransmitter systems, creating the regular 90-minute rhythm that structures our nights. All of this molecular machinery operates automatically, outside conscious awareness or control. You can't decide to increase your adenosine clearance rate, or manually shift your circadian phase, or voluntarily trigger REM sleep. The systems simply run, governed by ancient genetic programs refined over millions of years of evolution, producing the nightly phenomenon we call sleep with remarkable reliability. The glymphatic system clearing the brain. One of the most significant recent discoveries in sleep research is the glymphatic system. First identified in 2012 by Danish neuroscientist Maiken Nedergaard and her colleagues, and confirmed in humans through imaging studies published in 2024. While the existence of this waste clearance system is now established, researchers continue investigating the precise mechanisms by which it operates. The brain generates tremendous amounts of metabolic waste during normal activity. Neurons consume energy, produce byproducts, break down proteins, and generate various molecular debris. In most of the body, the lymphatic system handles waste removal, collecting cellular garbage and transporting it away for disposal. But the brain has no conventional lymphatic vessels. For decades, scientists wondered how the brain managed waste removal without this system. The glymphatic system provides the answer. Research has demonstrated that cerebrospinal fluid, or CSF, the clear liquid that surrounds the brain and fills its internal cavities, plays a far more active role than previously suspected. Rather than merely cushioning the brain, CSF flows through the brain tissue itself, following specific anatomical pathways. Studies show that CSF enters the brain along the outside of arteries, in spaces between the arterial walls and the surrounding brain tissue. These perivascular spaces act as channels, allowing CSF to penetrate deep into the brain. The fluid then moves through the tissue itself, mixing with interstitial fluid, the fluid that fills the microscopic spaces between brain cells. This interchange allows CSF to collect waste products from the interstitial fluid. Finally, the CSF exits along veins, carrying accumulated waste out of the brain and into the lymphatic system of the body, where it can be processed and eliminated. The name glymphatic combines glia and lymphatic because the system depends heavily on glial cells, particularly astrocytes. These star-shaped support cells have processes that wrap around blood vessels, and they express specialized water channels called aquaporin 4 or AQP4. Research has shown that AQP4 channels are essential for the efficient exchange of CSF and interstitial fluid. Mice lacking AQP4 show dramatically reduced waste clearance from the brain, demonstrating the importance of these channels. Here's what makes this discovery particularly relevant to sleep. The glymphatic system is dramatically more active during sleep than during wakefulness. A landmark 2013 study demonstrated that the extracellular space, the fluid-filled gaps between brain cells, expands by approximately 60% during sleep. This expansion reduces resistance to fluid flow, allowing CSF to move more rapidly through the tissue and clear waste more efficiently. During wakefulness, the extracellular space contracts, the system slows, and waste begins accumulating again. Evidence suggests that the neurotransmitter norepinephrine plays a crucial role in regulating this expansion and contraction. During wakefulness, high norepinephrine levels keep the extracellular space compressed. During sleep, particularly during slow-wave sleep, norepinephrine levels drop, the space expands, and glymphatic activity increases. Recent research published in 2025 has further demonstrated that rhythmic oscillations in norepinephrine during sleep help drive synchronized changes in blood vessel diameter and CSF flow, effectively creating a pumping mechanism that enhances waste clearance. Among the waste products cleared by the glymphatic system is amyloid beta, a protein that accumulates in the brains of people with Alzheimer's disease. Studies indicate that amyloid beta levels in the brain decrease during sleep, and chronic sleep disruption leads to increased amyloid beta accumulation in animal models. This suggests a potential mechanism linking poor sleep with increased risk of neurodegenerative diseases. Without adequate sleep, waste proteins accumulate over time, potentially contributing to disease development. The glymphatic system might help explain why sleep is universal among animals with nervous systems. The brain has no downtime for maintenance in the way other organs do. It must function continuously to maintain vital processes. Sleep provides a state where external demands are minimal, allowing the brain to prioritize internal housekeeping. The dramatic increase in the waste clearance during sleep suggests this housekeeping is one of sleep's fundamental purposes. Interestingly, research indicates that sleep position may influence glymphatic efficiency. Studies in rodents have shown that sleeping on one side produces better glymphatic clearance than sleeping on the back or stomach. Possibly because this position optimizes the anatomical configuration of drainage pathways. Whether this finding applies to humans remains under investigation, but it suggests that even seemingly minor aspects of sleep behavior might influence this critical system. The discovery of the glymphatic system represents a paradigm shift in understanding sleep's purpose. While researchers have long known that sleep was essential, the specific mechanisms making it essential remained elusive. The glymphatic system provides a concrete, measurable function that can only occur efficiently during sleep, offering a partial answer to the ancient question of why we spend a third of our lives unconscious. Sleep deprivation, when the system fails. The importance of sleep becomes starkly apparent when we examine what happens in its absence. Sleep deprivation produces a cascade of effects touching virtually every aspect of human functioning, from the molecular level to complex cognitive processes to long-term health outcomes. The effects begin almost immediately. After just one night of poor sleep, cognitive performance degrades noticeably. Reaction times slow. Attention wavers. Working memory, the ability to hold and manipulate information temporarily, becomes less reliable. People make more errors on tasks requiring sustained focus. They struggle more with complex problems requiring integration of multiple pieces of information. Even relatively simple tasks feel more difficult, requiring more effort to maintain performance. These cognitive effects worsen with additional sleep loss. Studies of total sleep deprivation, where people stay awake for multiple days, reveal progressive deterioration. After 2 days without sleep, performance on attention tasks becomes severely impaired, with frequent lapses where people essentially stop responding for seconds at a time. After 3 days, some people begin experiencing microsleeps, brief episodes lasting a few seconds where they essentially fall asleep with their eyes open, completely unaware they've done so. These microsleeps become more frequent with continued wakefulness and can occur during any activity, including driving or operating machinery. Extended sleep deprivation can produce more dramatic effects. People may experience visual distortions where objects seem to shimmer or move. Some report illusions, seeing things that aren't there, though usually recognizing them as unreal. In extreme cases, typically after 4 or more days without sleep, some individuals experience true hallucinations and even temporary psychotic symptoms. These symptoms resolve with sleep, but their occurrence demonstrates how profoundly the brain depends on regular sleep. The emotional effects of sleep deprivation are equally significant. Research consistently shows that sleep-deprived people exhibit increased negative emotional reactivity. They respond more strongly to frustrating or unpleasant stimuli, finding it harder to regulate emotional responses. The amygdala, a brain region involved in emotional processing, shows heightened activity in response to negative stimuli after sleep deprivation, while its normal regulatory connections with the prefrontal cortex weaken. Sleep-deprived people report more irritability, more anxiety, more sadness, and less ability to experience positive emotions fully. Even partial sleep restriction, getting insufficient sleep night after night, which is extremely common in modern society, produces cumulative effects. Studies show that restricting sleep to 6 hours per night for 2 weeks produces cognitive impairment equivalent to staying awake for 2 full days. Yet the sleep-restricted individuals often don't recognize how impaired they've become. They feel sleepy, certainly, but they don't realize the extent to which their performance has degraded. This gap between subjective experience and objective performance is particularly dangerous because people may engage in activities requiring full alertness while being significantly impaired. The physical health consequences of chronic sleep insufficiency are substantial. Epidemiological studies have linked chronic short sleep with increased risk of numerous health conditions. People who consistently sleep less than 7 hours per night show higher rates of obesity, likely due to sleep's effects on appetite-regulating hormones. Sleep deprivation increases ghrelin, which stimulates appetite, and decreases leptin, which signals satiety. Evidence also suggests connections between insufficient sleep and increased risk of type 2 diabetes, possibly related to sleep's role in regulating insulin sensitivity and glucose metabolism. Cardiovascular health suffers from chronic sleep deprivation. Studies indicate associations between short sleep duration and increased risk of hypertension, heart attack, and stroke. The mechanisms aren't entirely clear, but may involve sleep's effects on blood pressure regulation, inflammation, and stress hormone levels. Even one night of poor sleep can produce measurable increases in blood pressure the following day. The immune system also depends on adequate sleep. Research shows that sleep-deprived people are more susceptible to infections. In controlled studies, people who slept less than 7 hours per night before being exposed to a cold virus were nearly 3 times more likely to develop illness compared to those who slept 8 hours or more. Sleep appears essential for immune system function, with various immune processes showing circadian rhythms and sleep-dependent enhancement. Perhaps most concerning is emerging evidence linking chronic sleep insufficiency with increased mortality risk. Large epidemiological studies have found that people who consistently sleep less than 6 hours per night have higher death rates than those sleeping 7 to 8 hours, even after controlling for other health factors. The exact mechanisms remain under investigation, but the association suggests that chronic sleep deprivation has fundamental effects on longevity. These various effects of sleep deprivation underscore sleep's essential nature. Sleep isn't merely pleasant or restorative. It's required for normal human functioning at every level. The body and brain can temporarily compensate for some sleep loss, but they cannot do so indefinitely without consequences. Every system examined shows dependencies on regular, adequate sleep. The psychology of monotony and sleep. There's an interesting parallel between the monotony of sleep itself and what helps induce sleep. Sleep is, by its nature, repetitive and predictable. You lie down in the same place at approximately the same time and enter the same sequence of stages you've entered thousands of times before. This repetitiveness is precisely what makes sleep reliable and restorative. Research in cognitive psychology suggests that monotony and predictability have specific effects on consciousness and attention. When exposed to repetitive, unchanging stimuli, the brain gradually reduces its alertness. Novel or unexpected events capture attention automatically. This is an evolutionary adaptation, as novelty might signal danger or opportunity. But when nothing novel occurs, when the environment remains constant and predictable, maintaining high alertness serves no purpose and wastes resources. This is why monotonous tasks often induce drowsiness. Long highway driving at night, particularly on straight, empty roads, produces a hypnotic effect. The visual field remains constant, with the same patterns repeating endlessly. The sound environment is unchanging. The motor actions required are minimal and repetitive. These conditions create an ideal environment for decreased alertness. Studies show that drowsy driving is a significant cause of accidents, particularly in monotonous driving conditions. The same principle applies to lectures, meetings, or any situation involving sustained attention to unchanging stimuli. When information is presented in a monotonous way, the same tone of voice, the same pacing, minimal variation, the brain's arousal systems gradually downregulate. Attention wanders. Thoughts drift. Eventually, if the person is already somewhat sleep-deprived, they may doze off entirely. Sleep researchers and insomnia specialists use this principle therapeutically. For people struggling to fall asleep, standard advice includes making the bedroom environment as boring as possible. No television, no bright screens, no engaging books, nothing that captures attention or provides novelty. The bed should be used only for sleep and intimacy, creating a strong association between that location and sleep. The hour before bed should involve quiet, unstimulating activities that allow arousal levels to decline naturally. Some people find certain types of monotonous stimulation actively helpful for sleep. White noise machines provide unchanging acoustic input that masks potentially alerting sounds while offering nothing that captures attention. Similarly, some people find rhythmic sounds like rainfall or ocean waves conducive to sleep. The pattern is predictable enough not to be alerting, yet provides gentle, constant stimulation that may help maintain the state of drowsy inattention that precedes sleep. There's something almost meditative about deliberately embracing monotony. In a culture that values productivity, novelty, and constant stimulation, choosing to be bored feels countercultural. Yet research suggests that periods of low stimulation serve important psychological functions beyond just facilitating sleep. They allow mental consolidation, creative thinking, emotional processing, functions that suffer when attention is constantly directed outward toward novel stimuli. Sleep takes this to an extreme. During sleep, external stimulation effectively ceases to matter. The most boring possible state, perhaps. No sensory input, no conscious thought, no experience at all in the conventional sense. Yet this boring, repetitive, utterly mundane process is so essential that your body will force it to occur regardless of circumstance. No matter how exciting or urgent the waking world might be, eventually sleep will claim you, carrying you into hours of unconscious monotony, from which you'll emerge restored and ready to face the world again. Closing reflections. The unremarkable necessity. We've wandered through sleep's many dimensions tonight. Its history, its neural machinery, its stages and cycles, its molecular mechanisms, its cognitive functions, its consequences when lost, and its relationship to the experience of monotony. Through it all runs a common thread. Sleep's fundamental ordinariness combined with its absolute necessity. Sleep happens every day, as regular as sunrise, as inevitable as the tide. There's nothing dramatic about it. You lie down, close your eyes, and consciousness fades. Hours pass that you don't experience. Then consciousness returns, and you get up to face another day. The routine is so familiar that we barely think about it. Yet this ordinary process involves extraordinary complexity. Your brain cycles through distinct states, each with its own electrical signature, its own neurochemical environment, its own functions. Waste products accumulated during waking hours are cleared. Memories are consolidated and organized. Emotional experiences are processed and integrated. Immune cells mobilize. Hormones are secreted. tissues are repaired. The myriad systems that compose a human body conduct their nightly maintenance, each process timed to occur during specific sleep stages, coordinated by ancient mechanisms that evolved over millions of years. The fact that this all happens automatically, without conscious effort or awareness, doesn't make it less remarkable. If anything, it makes it more so. Evolution has crafted sleep as an automatic, self-regulating process because it's too important to leave to conscious control. You couldn't forget to sleep any more than you could forget to breathe. The homeostatic pressure builds inexorably, and eventually sleep will claim you whether you wish it or not. Modern life often treats sleep as optional, as time that could be better spent on productive pursuits. We celebrate those who sleep little, viewing their sleep deprivation as evidence of dedication or superior capability. But this attitude misunderstands sleep's nature. Sleep isn't weakness or waste. It's the foundation on which all waking function rests. Without adequate sleep, cognitive performance degrades, emotional regulation fails, physical health suffers, and even lifespan may shorten. Perhaps there's wisdom in sleep's very boringness. In a world of constant stimulation, of endless novelty, of perpetual demands for attention and engagement, sleep offers respite. It's a time when the external world fades, when novelty ceases, when monotony reigns. This external monotony allows internal processes to proceed uninterrupted. The brain can focus on maintenance rather than responding to environmental demands. The repetitive nature of sleep, the nightly return to bed, the predictable progression through sleep stages, the cyclical pattern repeating 4 or 5 times per night, night after night, year after year. This repetition is exactly what makes sleep work. The brain knows what to expect. The circadian clock coordinates timing. The homeostatic process builds pressure. The molecular machinery activates, and it all unfolds as it has countless times before, as it will countless times again. There's a certain peace in accepting sleep's place in life, in recognizing that this boring, repetitive, utterly ordinary process is also profoundly necessary and beneficial. You don't need to make sleep interesting or exciting. You don't need to optimize it endlessly or track every minute with technology, though understanding it can help you prioritize it appropriately. You simply need to allow it to happen, to give it the time it requires, to create conditions favorable for its occurrence. As you lie in bed tonight, or whichever night you listen to this, you might reflect on all that's happening or will happen as you sleep. Your neurons will fire in coordinated patterns, replaying the day's experiences. Adenosine levels will decline. The glymphatic system will clear waste from your brain. Your immune system will deploy its defenses. Hormones will be secreted according to ancient rhythms. Your memories will be sorted, some strengthened, others allowed to fade. But you won't be aware of any of this. You'll simply sleep, experiencing perhaps some dreams, perhaps nothing at all. And that's exactly as it should be. Sleep doesn't require your attention or effort. It requires only that you stop giving attention and effort to everything else, that you lie down, close your eyes, and let biology do what it has evolved to do. In a sense, sleep is the ultimate expression of trust in your body's wisdom. When you sleep, you relinquish conscious control, trusting that automatic processes will maintain vital functions, that you'll breathe without trying, that your heart will continue beating, that you'll wake again when morning comes. This trust is well-founded. The mechanisms governing sleep are ancient, robust, and reliable. They've kept our ancestors alive for millions of years, and they continue operating in you with the same dependable regularity. So perhaps we should stop viewing sleep as boring, or rather, we should recognize that its boringness is precisely its virtue. Sleep doesn't need to be exciting. It needs to be regular, reliable, and adequate. It needs to happen night after night with the same comfortable monotony. In this sense, boring is beautiful. Boring is healthy. Boring is exactly what sleep should be. As we close tonight's exploration, let your mind settle like dust after a gentle disturbance. The facts and concepts we've discussed might fade into the background, becoming less distinct, their edges blurring. That's fine. The goal wasn't to retain every detail, but to spend time considering sleep, to approach it with curiosity and respect, to recognize its importance even as we acknowledge its ordinariness. Your eyelids might feel heavy now. Your breathing might have slowed. These are signs that sleep is approaching, that the homeostatic pressure has built, that your circadian clock is opening the gate of sleep. There's nothing you need to do except allow this natural process to continue. No effort is required, no struggle necessary. Simply let go and sleep will come. If you've enjoyed this exploration of sleep's quieter dimensions, of the mundane science underlying our nightly rest, perhaps you'll consider subscribing to this channel. There's something oddly satisfying about delving into topics that lack flash or drama, about finding interest in the everyday mechanisms that keep us functioning. Psychology has no shortage of such topics, and we'll continue exploring them together in future episodes. But for now, let sleep come if it will. Let consciousness fade. Let the day recede into memory. Tomorrow will come soon enough, and when it does, you'll be rested, restored, ready to face whatever it brings. All thanks to the boring, ordinary, absolutely essential process we call sleep. Good night.